live! Hello, Kagglers. I'm just really quickly going to post to Twitter while I wait for the live stream to catch up with me and make sure everything's working okay. Howdy! We are going to be starting with a new paper today for the reading group. Okay, excellent. I had a second where I was like, did I forget to plug my mic in because I wasn't hearing anything? Starting now. We're starting a new paper. And we didn't do a vote for this one, for which, I don't know, we have been doing a vote for the last couple ones, but I spent some time thinking about it, and my experience of reading groups has been that they tend to be, I don't need this anymore, has been that they tend to be on a specific topic, and that the papers for the reading group are chosen in order to help whoever is in the reading group develop a deeper understanding of the topic area. So, the topic area that we've been focusing on lately has been the transformer, they're not all transformer, but neural language models, basically, in as much as you would call them language models. I think the last paper that we read had some distinction between more statistical language modeling and transfer learning trained on language that has the captures information about the distribution of words and how they occur together and in what situations, which I suppose I would call a language model. I'm just going to call them language models. And this paper, I think, forms a really important part of that conversation. So the point of this paper is to do some investigation and some model validation looking at these, specifically BERT. So we read the book BERT Paper a while ago. It's a transformer-based model. And really find out what qualities of the data the model is reliant on, and also to what degree it is acting as a good proxy of human language processing and understanding. So that's the sort of general point of this paper. Sina says, thanks for the tweet, otherwise I would have missed it. I try to remember. And hello, Himansu, Vijay, Ayush, and Archelius. Welcome to the live stream. So that's the point of this paper. And it's also been something that's had a lot of discussion around it in the NLP, I almost said the NLP universe, like we're wrestling fans, the natural language processing research community. So I think it's an important paper to read, to put the other work that we've read into context. That's the whole thing. And the paper title is, and it should be linked in the description box if you want to read the paper along with me. Sip of tea. Could use a little bit of caffeine today. Oh, and this mug is actually, it's a linguistics mug. It's the Berkeley Linguistic Society. So the paper is called Probing Neural Network Comprehension of Natural Language Arguments, and it's by Timothy Niven and Hongyu Cao from the National Cheng Kung University in Tainan, Taiwan. So, and Timothy Niven sounds very, very familiar. I don't know if I know him. These names might just seem familiar to me because I've read a lot about this paper and their names have been used around it. So, hello, everyone who has joined. Very long Gmail address. Yeah, I think this is just sort of his, I'm assuming his address for correspondence. So, let's get into it. Abstract. We are surprised to find that BERT's peak performance of 77% on the argument reasoning comprehension just one task, reaches just 3 points below the average untrained human baseline. However, we show that this result is entirely accounted for by exploitation of spurious statistical cues in the dataset. So basically they're saying BERT has like almost human levels of performance, and that's astounding, and they did some additional investigation and found that this wasn't because there was good This wasn't because BERT understands language in some sort of human-like way. It's because the model relies on the statistical cues in the data set itself. Sorry, I was trying to find my place. We analyze the nature of these cues and demonstrate that a range of models all exploit them, so it's not just BERT. This analysis informs the construction of an adversarial data set on which all models achieve random accuracy, but presumably a human would be able to handle pretty well. Our adversarial data set provides a more robust assessment of argument comprehension and should be adopted as the standard in future work. So what they're saying here is that the reason these models are doing so well on this particular task is not because they have a deep understanding of or even any understanding of the process, the reasoning behind the task. It's because the way that the data set is constructed, there are always cues in terms of the statistical distribution of the words, and if you remove those cues, none of these models, again, that I would call language models, do better than chance. And hello to everyone who's joining. I'm not gonna butcher y'all's name. 9 a.m. in the morning, first thing. Well, for me, but welcome. Okay. And I think we're going to get a little bit more of a discussion of what this argument reasoning comprehension task is, so I'm not going to go and Google that now, but we might if we need more. Andy says, should be adopted as a pretty aggressive assertion. I would agree. I don't think they're saying replaced. I think it's fine to evaluate on this other data set, but they're saying that they have evidence that this data set that doesn't use those cues is a better metric for evaluating the ability of these models to do this specific task. So, I mean, yes, it's a little bit of a strong claim. I will say, I think I usually try to say this. This was published in the proceedings of the most recent ACL in Italy. Yeah, here we go, in Italy. So this was a peer-reviewed paper. ACL is a pretty hard conference to get into. So this is, work that has, not all ACL papers are going to be unilaterally of the same quality, but in general, I think this paper has passed some pretty rigorous analysis by other people in the field, and also it's one that a lot of other researchers, especially after ACL, have begun talking about and suggesting that we adopt. So I think it's important especially if you're working in NLP, it's important for you to know about. So, all right, introduction. Argumentation mining is the task of determining argumentative structure in natural language text, e.g., which text segments represent claims, like this should be adopted as the standard in future work, that's an example of a claim, and which comprise reasons that support or attack these claims, and there's some citations here. This is a challenging task for machine learners, as it can be hard even for humans to determine when two text segments stand in argumentative relation, as evidenced by studies on argument annotation. So here we have a human litmus test, humans doing this task and showing that it can be a very challenging task. Our approach to this problem is to focus on warrants from Tolman 1958, a form of world knowledge that permits inference, and that's logical inference. Consider the simple argument: it is raining, therefore you should take an umbrella. The warrant, it is bad to get wet, could license this inference. Knowing 3, that you don't want to get wet, facilitates drawing an inferential connection between 1 and 2, right? So you could imagine, several steps. I'm going to finish this paragraph and then I'll come back to that thought. However, it would be hard to find it stated anywhere since warrants are most often left implicit, Walton 2005. Thus, on this approach, machine learners must not only reason with warrants, but also discover them. So one of the warrants here is it is bad to get wet. I guess another warrant here is that you are going to be outside when you leave. If you are leaving and you're going to go through like a tunnel system to a different building, you don't need to take an umbrella. So that's a warrant that's not stated, but you need to know and understand in order to draw inference between statement 1 and statement 2. If that makes sense? Yeah. Sorry, I'm just catching up on the comments, making sure no one's adding things that we should talk about right now. So it's a difficult task and a lot of sort of, I don't know, if you've had a lot of training in academic writing, actually, if you're interested in academic writing, I recommend. Scooch. Oh, it's green. Oh, no. I recommend this book, They Say, I Say, by Gerald Grath and Casey Birkenstein. And a big part of this book, which again is a little bit see-through because I used some green on the cover, is that constructing that argumentative structure and being like, here's what one person says, here's sort of the assumptions that they made, here's the assumptions I agree with, here's the assumptions I disagree with, the warrants that you are required to accept in order to accept their inference. So this is a lot of sort of like logic and rhetoric, and I don't want to get too deep into it, but that's the general structure of the problem. Tina says, warrant can be explained, though. It can be, but it's not necessarily going to be explained in the text. Here we go. So talking about the tasks, there's a data set for this. The Argument Reasoning Comprehension Task, ARCT, Habernal et al. 2018a, defers the problem of discovering warrants and focuses on inference, so you're not trying to extract the warrants from a text. An argument is provided comprising a claim, C, and reason, R. The task is to pick the correct warrant, W, over a distractor called the alternative warrant, 8. The alternative warrant is written such that the reason and the alternatives are, conjuncts? They can't both be true. An alternative warrant for our earlier example could be, it is good to get wet. So it is bad to get wet, plus it is good to get wet is like all of the ways you could feel about it. In which case we have what's the hat? One sec. That's why I keep all my textbooks right near me. I think there's an appendix in here with all the symbols, and I could be wrong about that. What's the pokey one? It's definitely in the first couple chapters. If you haven't had semantics courses before, that's a lot of formal logic. And I'm a little bit rusty, I will admit right now. Quantifiers. I'm just looking for a definition of the symbol. Sina says, and. Yeah. Okay, so it's the conjunct. So the disjunct is this little guy. I don't know if you can see. The disjunct is the down arrow, and that means sorry, I'm just going to read some stuff. Sorry about that, but this particular task is a little bit out of my wheelhouse. So conjunction here is written as the ampersand. Interesting. Okay, so it looks like they're actually using a different citation, or a different, like, little set of symbols than I was trained with. But I guess that makes sense because it's the reverse of disjunct. And then, this is helpful. There's two common symbols for negation. So one is this one that looks like an edge of a shelf, and another one is the tilde. And this book uses the tilde, but that one does not. The disjunction connective, so the opposite of this one, is commonly glossed as and/or described as inclusive disjunction. The symbol for disjunction is the downward facing arrow guy. A local disjunction is true if either or both of the combined prepositions is true. Okay, so this one, so the claim, so if the reason and the warrant are both true, the claim is not true. Sorry, that was a lot of reviewing for me. So if the reason and the alternative are both true, then the claim is not true. But if the reason and the warrant, so the correct one, the one that you should be able to guess, are both true, then the claim must also be true. So that's sort of the direction of inference that you're doing. Yes. And here says, the reason in conjunction with the alternative means is not the claim. Yeah. Okay, I think we got there together. All right. So you want to pick the warrant that makes the claim be true, not the alternative, which will make the claim not be true. So here in this example, the claim is that Google is not a harmful monopoly. The reason is that people can choose not to use Google. So if these are both true, then it cannot also be true that all other search engines redirect to Google. So if all search engines redirected to Google, then there would be no way for you to choose not to use Google. So those can't be. So the alternative and the reason, if those are both true, it cannot be that the claim is true. If the reason and the warrant are both true, the claim must be true. So if people can choose not to use Google and other search engines don't redirect to Google, then Google is not a harmful monopoly, is the structure of the task. All right, sorry, that was a lot of reviewing semantics for me. All right, so that's the task. The specific task is the ARCT SemEval shared tasks. So shared tasks are kind of like Kaggle competitions. There's a shared data set and everyone's trying to optimize for the same thing. Verify the challenging nature of this problem. Even supplying warrants, learners still need to rely on further world knowledge. For example, to correctly classify the data point in Figure 1, it is at least required to know how a consumer choice and web redirects relate to the concept of monopoly and that Google is a search engine. So there's a lot of other things that you need to know to make that work. All but one participating system in this shared task could not exceed 60% accuracy on binary classification. So if you are just guessing, you would get about 50% accuracy. So 60% accuracy is not that good. 60% accuracy. Sorry, I keep losing my place. It is therefore surprising that BERT, Devlin et al. 2018, achieved 77% test set accuracy with its best run, Table 1, only 3 points below the average human baseline. Untrained. So this is someone who hasn't had a lot of formal semantics training and it's just, you put these things together and like, if these statements are true, which of these other ones must also be true, sort of thing. Without supplying the required world knowledge for this task, it does not seem reasonable to expect it to perform so well. This motivates the question, what has BERT learned about argument comprehension? So sort of related to this, and I don't know if they're going to talk about it, a lot of the text generation with things like GPT-2. Let's see if I can, I think it was, there's a website, I think it's called Transformer to Text, maybe? Talk to Transformer. So if we wanted to do something like, actually, let's do the first couple sentences of here. So if we paste in, no, that's not what I wanted to do. So if we paste in some text, then, and this is generated using GPT-2, which we also read the paper for, the text that is generated given that other text does seems to have some sort of knowledge of the world that relates to it. So we could say, So given all these statements, the target is a problem that allows the investigator to discover warrant W over a relevant target A, such as a state of mind. In the case of the present study, a valid answer to the question is it right to kill an American citizen? And to identify the difference between the target and its warrant W. So this is just generated text. But just looking at this, you might be like, okay, I think this model has some understanding to some degree of semantics, basically, because it's able to generate text that seems like it's from a very similar genre. So I think that there's a desire, you know how like humans see faces everywhere? I think there's a desire to see the output of models as being human-like, even though it's not generated by the same sort of like cognitive processes that humans have. And this paper is really trying to get at what is the model understanding? What is it relying on to generate these really impressive results? So I know this is a lot of sort of like philosophical discussion of what it means to be human and how language models, the class of things that I'm calling language models, that other people might disagree with me about being called language models or not, differ from that. So table 1, baseline and BERT results. Let me zoom in a little bit. Our results come from 20 different random seeds, plus or minus gives the standard deviation. The mean for BERT large is skewed by 5 out of 20 random seeds for which it failed to train a problem noted by Devlin et al. If you'll remember in the paper, it's like sometimes it doesn't work and you just have to start over. We therefore consider the median a measure of BERT's performance. The mean of the non-degenerate runs for BERT large is 0.716 plus or minus 0.4. So if we zoom in a little bit, you can see that a trained human is pretty close to ceiling. We're getting, so this is the standard deviation, so many people will get everything right, and it seems to be that you're pretty close to ceiling once you've been trained on this task. An untrained human is right about 80% of the time, give or take. BERT has quite a bit of variance, and again, they mentioned that some of the runs were degenerate, so when they tossed those out, they got performance of around 71%, and then the best run was around 80%, which again is about where humans are, roughly. And then GIST, which I'm not familiar with, Choi and Lee 2018. BERT, the base model. World knowledge, again, not familiar with that. BOV, bag of verbs, maybe? And then bidirectional LSTMs, presumably with attention. That's been a very common type of model to use in NLP problems for a couple years now. So. And these models are doing not so hot. Actually, the BiLSTM is looking like it's kind of close to chance. Because remember, this is a binary choice, so 50% accuracy is you are just guessing. And the other models are also not doing amazing. The one that looks like it's doing the best is this GIST model, which I, again, not familiar with. 2018. GIST at SemEval 2018 Task 12, a network transferring inference knowledge to argument reasoning comprehension tasks. Okay, so it's a SemEval paper, not a workshop that I tend to follow super closely. All right. So how are they going to do this? They want to figure out if the model is capturing the things that a human would in order to get human-like performance, which again, if you're trained on this task, is near ceiling. Quarky says, what book is this? So this is actually a paper, and the paper is Probing Neural Network Comprehension of Natural Language Arguments by Nevin and Cow from the 2019 ACL meeting in Florence that just happened. So this is a pretty recent paper. To investigate BERT's decision-making, we look at data points it finds easy to classify over multiple runs. Habernal et al. 2018b performed a similar analysis with the SemEval submissions, and consistent with their results, we found that BERT exploits the presence of keywords in the warrant, especially not. Though probing experiments designed to isolate such effects, through probing experiments designed to isolate such effects, we demonstrate in this work that BERT's surprising performance can be entirely accounted for in terms of exploiting statistical spurious cues. So what they're saying here is that BERT isn't modeling argument structure in any way, which I think is not super surprising. We wouldn't expect a sort of, it's not really a statistical language model, but we wouldn't expect just a language model basically to be able to model argument structure and capture these rich semantic relationships. Basically, they're saying that BERT is a not detector in terms of this task. And when you do fine-tuning, you're training it to notice whether there's the word not or not. However, probing experiments, so what they call probing experiments here, some people were talking about on Twitter, and I'll see if I can, remind me, and I'll see if I can find the link. The word probing experiments generally refers to something else, and I don't know what the other thing is, but there was some grumbling over this particular use of terminology, so FYI. And Quirky says, Wikipedia has a page list of logic symbols. Oh. No, I didn't want to make it bigger. Oh, very helpful. Thank you. Oh, here you see. So the this guy and also the tilde, which is what they use in used in my textbook. Okay, so conjunction and then disjunction. All right. Helpful. Thank you. All right. However, we showed that the major problem can be eliminated in ARC. So they found this problem. I'd say it's a problem more with the data set and the ability of the data set to evaluate models' ability to, not the ability of the data set, the appropriateness of the data set to evaluate models' ability to model argument structure. And they are also using those same tests to show that the data set that they've constructed doesn't have that problem. So the major contribution of this paper is a data set. It's a data set paper, but also this way of evaluating models. Since the disjunct of R and A implies not C, we can add a copy of each data point with the claim negated and the label inverted. Oh, I see. So what they're saying is that we could have a copy of this problem, where instead of saying Google is not a harmful monopoly, we say Google is a harmful monopoly. And in that case, the warrant and the alternative would be switched. So if Google is a harmful monopoly, the warrant must be that all other search engines redirect to Google. And it cannot be that other search engines don't redirect to Google. So what they're saying is that they change the direction of the claim and then switch which are the warrants and which are the alternatives. That's really clever. That is some clever data augmentation. 10 out of 10. Hell yeah. This means the distribution of statistical clues in the warrants will be mirrored over both labels, eliminating the signal. Yeah. Oh, this is a good paper. On this adversarial data set, all models performed randomly, with BERT achieving a maximum test set accuracy of 53%. That's not good. Sorry, that's not good performance on a binary choice task. But I think that is good in that it is demonstrating basically that BERT is acting as a not detector in this particular instance. Oh, Kova said conjunct, not disjunct. Thank you. The adversarial data set therefore provides a more robust evaluation of argument comprehension and should be adopted as the standard in future work in the data set. Oh, sorry, Mohammed. He said I swore. I'll try not to do that. I just got excited. It's cool. All right, and now we're probably going to get a little bit deeper into the evidence for this, but that's sort of the basic claim of the paper. All right. Task description and baselines. Let I equal 1 through n, index each point in the data set curly d, where the set of d equals n? Okay. The two candidate warrants in each case are randomly assigned a binary label, j, from 0 and 1, such that each has an equal probability of being correct. The inputs are representations for the claim CI, reason RI, warrant 0, W0I, and warrant 1, WI1. Gutham says Bertham is not detector. Can you explain that? So what they're saying, when I say not detector, what I mean is based on their findings that what BERT is, the information that BERT is using to achieve this really high performance on the task is whether or not the word not occurs in the warrant. Because you can imagine if you're putting together a data set like this, I think it makes sense to have like one warrant has the word not in it and the other one doesn't, and they're sort of the inverts of each other, so that A implies not B. What's that relationship? Anyway, so whichever one has not in it is either more or less likely to be the correct warrant, and BERT is exploiting that statistical anomaly. And well, presumably they're going to talk about it in a lot more depth. Sina says, size of D. Oh, okay, so the size of D is N. Oh, we're just using I as the index for our data set D. That makes sense. Kova says, I wish I could follow the logic in the mirroring. I cannot. Oh, the logic in the mirroring? Well, I'm assuming we'll come back to it when we get a little bit further down and they talk about their adversarial test set. Yeah, we'll dig down into it a little bit deeper. So we'll have another crack at it a little bit later on. Yeah, thank you when people are helping me with the notation. Thank you. I appreciate it. I spent a lot of my graduate career very frustratedly, like, texting. I have a friend who is in a math PhD program, and I just text him pictures with like of a textbook with like one of the symbols circled. I was like, Nick, help! Nick, what does it mean? I can't find it online, Nick. And then he dropped out of the math program, and I felt bad doing that. So thank you for being my math friends that I can text questions to. All right. So we've got our data set. For each point in the data set, we got a claim, reason, and 2 warrants. The label Y is a binary indicator corresponding to the correct warrant. So if warrant 0 is the correct warrant, it has the label Y. If warrant 1 is the correct warrant, it has the label Y. Okay, that makes sense. The general architecture for all models is given in figure 2. Shared parameters theta, or theta as some people say, are learned to classify each warrant independently with the argument, yielding the logits. So Zji, where Z is, I think, oh, okay, so Z is the logit probability of the the 0 or the first warrant being the correct one. Let's look at the figure first. So the idea is that we have, in our data set, for each data set point, we take a little triple with the claim, so this is for I, the claim I, the reason I, and then a second one with the claim I and the reason I. And then the first one has warrant 0, and the second one has warrant 1. So these are the same claim and the same reason, but different warrants. And then we learn parameters theta, or theta. And then that gives us the logit, so basically the probability that we think that, well, it's not really a probability, but the weights assigned to either warrant 0 or warrant 1, and then we take the softmax of those, and then that's a probability. So which one we think is more likely given our trained parameters. Logits are independently calculated for each argument warrant pair, and then concatenated and passed through softmax. Okay, and then the label Y is going to be the one that we use to evaluate that final softmax and say whether it's correct or not, and then presumably do backpropagation and update our weights. Well, I think theta here is each of these models that they talked about separately. I think so. Okay, that makes sense to me. Hopefully you guys are following along. So this z that we get out, so for the ith element, the jth z, so j from a set of 0 and 1, is theta of ci, ri, wi, j. So either the 0th or the first, and then this j will be the same. These are then concatenated and passed through softmax to determine a probability distribution over the two warrants. Probability for I is the softmax of z0i and z1i, so for warrant 0, warrant 1. The prediction is then y hat of I, argmax j of pi, where j is one of these. So we pick whether we think that 0 or 1 is the correct warrant. The baselines are bag of vectors. That makes a lot more sense than bag of verbs. So remember we saw this when I was like, I don't know what that is. It's a bag of vectors. That makes a lot more sense. So it's like a bag of words, except the words are vectors. And it's not just the verbs for some reason, because I thought that made sense. Aww. Bidirectional LSTM from Hochreiter, H, and Schmidhuber. H and S by LSTM. The semi-vowel winner Gist, Choi and Lee 2018. Oh, so that's why they brought it up. So this is the model that got the best performance in the shared task. So this would have been like the winning Kaggle model if the shared task were a Kaggle competition. The best model of Botchin et al. 2018 and human performance. So we saw that in the table. For all of our experiments, we use grid search to select hyperparameters. Oh, I probably would have used random search. Dropout regularization and atom for optimization. Oh, I don't know, if you're doing model comparison, is grid search more fair? Because you could just, if you were using random search, you might pick a set of random points that happen to have better, well, it's true of grid search too. I don't know, I don't have strong intuitions here, except that I have been told that random search is generally preferable to grid search. We anneal the learning rate by 1/10 when validation accuracy drops. So they have a decaying learning rate. The anneal. I wonder if that means that the learning rate goes to 90% of the learning rate, or the learning rate goes to 10% of the learning rate. I'm only really familiar with the word annealing from like metalworking. It's when you heat the metal up and then cool it down so that all the crystals are pointed in the same direction and it becomes more malleable. Because as you manipulate metal, it becomes brittle. I used to be apprenticed to a jeweler. If I hadn't gotten a scholarship to go to college, I'd probably be a jeweler right now. So that's a fun Rachel fact. The final parameters come from the epoch or epoch with maximum validation accuracy. Okay, so they're picking the best epoch or epoch. Bag of vectors, not bag of verbs, and by LSTM inputs are 300-dimensional glove embeddings trained on 640 billion tokens, the Pennington one's super standard. Code to reproduce all experiments and detailing all hyperparameters is provided on GitHub. So if you were feeling it, I don't know why I can't click on that link. Nope, I can't. It's a non-clickable link. So if you're feeling it, you could check out their code on GitHub and reproduce some of their work. So 10 out of 10 reproducibility. Big fan. And then their BERT one, which is going to be a little bit more tricky in terms of architecture. Our BERT classifier is visualized in figure 3. This dude. The claim and reason are joined to form the first text segment, which is paired with each warrant and independently processed. Okay, so they're training like two BERT models independently. The final layer, CLS vector. CLS. Oh, that sounds like something that was in the BERT paper that I've forgotten about. Is passed to a linear layer to obtain the logits ZJI. The whole architecture is fine-tuned. The learning rate is 2e to the negative 5, and we allow a maximum of 20 training epochs or epochs, taking the parameters from the epoch with the best validation set accuracy. We use the Hugging Face PyTorch implementation. Oh, that one came out pretty recently, so this is, they were working quickly on this one. Okay, CLS vector. Let's check this out really quick. So, oh, that's right. I remember what that is. That is the, sorry, I shouldn't clap in the mic. Hope you're awake now. That is the token that they use that's like the label. Remember? So when they were doing classification problems, it's the token that tells you what the correct classification is when you go back. So it looks like they're doing the claim and reason separately, and then the SEP token, which distinguishes the input from the output. Fet1 says, are bag of words the same as bag of vectors? No, because bag of words don't necessarily need to be vectors. A lot of older NLP techniques in particular don't use vector spaces. They use things like co-occurrence. So, good question. Good question. Okay, so input, output, the token that tells us whether this is the correct one or not, I believe, and then the output of the whole BERT is the weight assigned to that label, so whether or not we think it's the correct label, and then that's the logit that they use here that goes into softmax. And so they're training, so they run BERT, so the warrant 0 and warrant 1 have separate independent modules. Not modules, but like independent architectures. Mohammed says, I'm super late to the party. Is this kind of related to GPT-2? A little bit, in that you could use the same model to evaluate GPT-2, the same method to evaluate GPT-2. The idea is that we are evaluating how well these big, again, I'm calling them language models. People probably wouldn't call them all language models, but I am, gosh darn it, are actually understanding things like argument structure and to what extent they are statistical knowers, right? Here's a really good example for this. If you've ever taught a kid to read, you know how they'll kind of get it, but then they'll get a little bit tired and they'll just start guessing words based on the picture in the picture book. I don't know if any of you have had this experience, but there'll be like a picture book of like, I don't know, a bunch of animals, and the kid will be reading, and maybe the sentence is all the animals are in the forest, and they might look at it and maybe there's some tigers in the picture and they're like, the tigers are in the forest, and you're like, no, you didn't read the words, you guessed. I think it's a little bit similar to that. Anyway, a little bit of a tangent. So that's their BERT architecture. Devlin et al. Report that on small data sets, BERT sometimes fails to train, yielding degenerate results. ARCT is very small with 1,200 training observations. Yes, that is small for modern NLP. I tried to get a paper published with about that many training points, and I did not have success. In 5 out of 20 runs, we encountered this phenomena, seeing close to random accuracies on validation and test sets. And I think we still don't really know why, unless there's a paper that's come out that I've completely missed. These cases occurred where training accuracy was also not significantly above random. Removing the degenerate runs, BERT's mean is 71.6 plus or minus 0.4. Remember, humans are around 80, which would beat the previous state of the art, as would a median of 71.2%, which is a better average than the overall mean since it is not skewed by the degenerate cases. However, our main finding is that these results are not meaningful and should be discarded. In the following sections, we focus on BERT's peak performance of 77% to make this case. So basically what they're saying here is we made a good go of it. We tried to train our model as best we could. We did end up beating the previous state of the art on this specific data set, but when we dug into it a little bit and we perturbed the data set in a way that would, foil some statistical guessers, we saw performance go down. So, a little sip of water. Nope, this is tea. All right. Now we get to the meat of it. Why is BERT doing so well? Statistical cues. And BERT, and I think also a lot of the different related models also did fairly well in this task, like Transformer XL, I think did okay, and other ones. A major source of the spurious statistical cues in ARCT, actually I do have a question that I really quickly want to answer, is ARCT in glue? Or was it one of the ones that they looked at? Shoe medium. Oh, this is literally just a blog post about this paper. Glue data sets. Glue benchmark. Yeah. What are the tasks? Linguistics acceptability, Stanford Sentiment Tree Bank, Microsoft Research Paraphrase Corpus, Semantic Textual Similarity Benchmark, Core Question Pairs, Multi-NLI Matched and Mismatched Question NLI, Recognizing Textual Entailment, which is sort of similar, Winograd NLI, which I believe is the hardest data set in the benchmark, and then Diagnostics Main. Okay, so this ARCT data set is not part of the GLUE benchmark. Sorry, I just had a sudden bug in my ear about it. Gotham says, so BERT is actually good, but just bad at argumentative reasoning tasks. It's a tool, right? And it's good for some things, but I think there's a desire for, I think there's a desire for us to see human-like patterns of behavior in things like language models, and to be, especially if you're impressed with something like text generation, be like, oh, okay, because you can generate text that looks like a human might have generated it, clearly you have a human-like understanding of language and the world, and that's not necessarily the case. So, oh wow, that's a lot of discussion, W on method brought up. The history of science might be helpful. It's traced on the closed procedure. And we've talked quite a bit about BERT on this channel. So it's not trained on a linguistic task at all. Closed procedures are known in literary science, where they've been used since the 1970s. Also, if you've taken a lot of standardized tests, you've definitely done them as a human. It's not clear the leader learns by solving them. It seems that you don't learn text immanent semantics. You learn things like co-occurrence statistics. Instead, you learn what Wolfgang Iser called Apple Strukturen. Oh, you can tell how much German I know. It's none. And negation is the strongest one of those that there is. Yeah, okay, that is very helpful. Thank you. Fet1 says, could you please cast some light on model selection? How we know whether we go for grid search, random forest, or whatever? Should we do trial and error to select our model? So random forest is a family of algorithms. I don't want to get too off track. Grid search is a way of defining your hyperparameter search space. In general, my current understanding, and again, I read a lot about machine learning, but I wouldn't call myself a primary machine learning researcher. My current understanding is that random search will generally converge better than grid search. Take that as you will. This is something that I'm thinking about quite a bit these days, and stay tuned is what I will say about model selection. And Kovis says, so BERT is good with keywords such as not, but when take that out and shape the argument differently, it performs bad. Yeah, that's basically what this whole paper is about. You have summarized it very succinctly. And Devin Chu says, a beginner here, and most of these things are going over my head. Yeah, I could see that. There's definitely, there's a lot going on here. And we have read, in the reading group, we've read a lot of the papers that this paper is talking about. So if you have time and are interested, you can go back and watch those ones, and hopefully we'll get a little bit of a better understanding of what's going on here. But I think basically Kovis has very succinctly summarized the paper. So if you're picking that up, I think you got it. All right. Statistical cues. Where are they coming from? The major source of spurious statistical cues in ARCT comes from uneven distributions of linguistic artifacts over the warrants, and therefore over the labels. This section aims to demonstrate the presence and nature of these cues. We only consider unigrams and bigrams, although more sophisticated cues may be present. To this end, we aim to calculate how beneficial it is for a model to exploit a cue K and how pervasive it is in the dataset, indicating the strength of the signal. So basically, if you were going to just guess based on the presence of words and bigrams, so unigrams are single words, bigrams are two words that occur next to each other, what words would be the most helpful? Oh, and now we're going to say it with math. And Kovis says, thanks. I actually wrote that logic on paper and went through it step by step. Oh, that's a great way to do it. All right. Formally, let fat T. I don't know. I don't know what you would call that symbol. J, I, be the set of tokens for data point I in our data set curly D with label J. We define a cue's applicability alpha K as the number of data points where it occurs with one label but not the other. Okay, so alpha K is the sum across all of the points in our data set. Why is this a 1? Why is this here? I don't know what this 1 means. Normalized, I guess? Maybe there's a 1 there. So for each pair of J and K, so K are the words or bigrams, or you could imagine doing other things in the future. J is the label. In the set of this guy, the set of tokens in the warrant for data point I with label J, and the disjunct, conjunct, or the K not in the set of T not J. Oh, okay. Let's take our time. I don't know why I take my glasses off when I'm thinking hard. Okay, so Ti not J. So label J would be true. Right? Okay, so let's say that we have a specific warrant. So we're looking at the words that are not in the set with the other label, because there's only 2 labels, so not J would be the other one. So these would be the words that don't show up when it's false, and the words that do show up when it's true. That has to be the conjunct. Yeah, Kovis is like, it's the conjunct, thank you. And then we're taking the each. So we're taking the sum of all the ones where it's true. That can't be it. Samuel says, I think the 1 just means that you add 1 if this condition is fulfilled. Oh, okay. So we're evaluating this whole thing. So where K is in the 1 label and is not in the opposite label, for each of those we add 1, and we do it over all, but what if it shows up? Okay, this must mean is in the set. Okay, so if it shows up in both of them, we don't count it. If it shows up in only the one where it's true and not the one where it's false, we don't count it. And then we do that for all the labels for a specific word or bigram. So what we're doing is, I'm getting there, we're getting there. So what we're doing is we're going through our data set for each set of warrants. We look at if the word does incur in the true warrant and doesn't occur in the false warrant, and if that condition is correct, we add 1, and then we add those all the way around. So, and it's the sum. So the number will be bigger the more often the word is used in the correct warrant and is not used in the false warrant. I think so. All right. Kova says FAT1, thank you, is an indicator conjunct function. I looked it up in the list of mathematical symbols on Wikipedia. That's thinking with, I was going to say portals, but it's not portals. Web portals, I guess. Okay. The productivity of a queue is defined as the proportion of applicable data points for which it predicts the correct answer. Are these exactly the same? Yes, they definitely are. Okay, so these are all of the times that it predicted the correct answer, and then here divided by all of the times that the word occurred. Wouldn't this just be 1? EJKETI, not da. Oh, wait, nope, there's an extra term here. And we're only going to count it this time if J is the correct answer. Okay, so this is basically how often it occurs in one and not the other. And here we are only counting it if it's the correct answer, not if it only occurs in one or the other. Okay, gotcha. Finally, we define the coverage. I don't know what that letter is. That looks like Arabic. It's probably Greek. I'm going to call it E-tail. Coverage E-tail of K of a queue as the proportion of applicable cases over the total number of data points. So this is how often the word shows up, basically. So this is a measure of frequency. In these terms, the productivity of a queue measures the benefit of exploiting it, while coverage measures the strength of a signal it provides. So if it's always going to tell you the correct answer, it's very reasonable to use it, but if it only occurs in 2 total items, it's not going to give you a very strong signal. Samuel says, since it says exists, exists is this. Woohoo. That's the existential modifier. I think the number would just be 1 if there's at least one warrant where the queue is helped. And Quarky says it is zeta, helpful. And Gautam, I'm pretty sure the times are on the YouTube community tab for the channel, but the paper reading is at 9 a.m. Pacific time on Wednesdays, unless there's another event going on. So, and everyone's like, it's zeta, thank you. Wait, are zeta and zeta different letters? I think they might be different letters. Zeta. Cena's like, it's, and then pasted the letter. Thank you. Very helpful. That tells me how to say it. All right. With m labels, if pi k is greater than 1 divided by m, the presence of a q is going to be useful for the task, and a machine learner would do well to make use of it. So this is just a nice way of formalizing the utility of a given q. And this, for this example, it is specifically for unigrams and bigrams, so words and pairs of words, but you could use it for any q you had in a problem. The productivity and coverage of the strongest unigram q we found, is given in table 2. It provides a particularly strong training signal. While it is less productive in the test set, it is just one among many such cues. We found a range of other unigrams, albeit with less overall productivity, mostly being high-frequency words such as is, do, and are. Bigrams that occurred with not, such as will not and cannot, were also found to be highly productive. So productive is really good at separating the true answer from the false answer. These statistics indicate the nature of the problem. In the next section, we demonstrate that our models are in fact exploiting these cues. So if we look at the productivity and coverage of not, so just like a single word, across the whole data set, if you pick the warrant with not, you will be right 61% of the time, which covers 64% of all data points. And if we look at the mean on the test data set for these models, you can see that gets you, that very simple cue gets you better than the previous, the previous state of the art was this GIST model, but it gets you, significantly better than bidirectional LSTMs, presumably with attention, which again have been a very popular model in NLP for the last several years. So, yeah. Where was I? Gotta find my place again. All right, so it is 10:02, so I'm going to call that for today. But I think this hopefully answers, I think Kovis had a question about what it means to be a not detector. So I guess it's not fair to say that it's a not detector. It appears that the BERT model, and we'll talk more about the experiments later, and presumably other similar models are really good at finding these statistical cues and exploiting the most productive or most discriminative features that have the largest coverage or occur most often. So, yeah. All right, so we are not actually going to be back with this paper next week. Next week is the last week of the SQL summer camp, so we'll be talking about SQL. I think next week at this time we're going to be talking about window functions. Window functions are great, super duper useful. So I mean, if you tune in, you'll learn something about SQL. Maybe, unless you already use window functions, in which case it'll just be like a nice review. But we will pick back up with these 2 weeks from now, and we'll start with this section here on the probing experiments. So far, I am really enjoying this paper. I think it's I think they're good questions to ask, like what are the limitations of these models? What do they work well for? What do they work poorly for? And I don't think anyone would say that like, oh, BERT's a bad model, we're going to throw it in the trash. I think it's just important to know when it is useful to use and when it's going to get you good results in the way that you want to be getting good results, and when it's going to get you results that are going to be maybe a little bit frustrating based on your desire. Oh, and people are saying that it's not zeta, it's maybe chi or XICK maybe? Yeah. So again, it's all Greek to me. Thank you for joining, everybody. I hope this was informative. I'm really enjoying this paper. And I will see you all on Friday for live coding. And this time, last week we sort of figured out what the visualizations, what information we would use in our visualizations in our summary. And this week we're actually going to make them. So there'll be some nice pictures from our text summarization project. All right. And I will see you all then. Thanks for joining, and I will see you on Kaggle. Bye.